Okay, question 4. So got something on your astronomy unit. Sun's got a mass of that number. White dwarf's got a mass of the other number. Calculate it, and it just says, just do what it says. Do that thing. So mass of the white dwarf divided by the mass of the sun. Best way of doing this is make sure you use that on your calculator, and make sure you use the 10 times 10 to the x button, and then it's put it in. That's the only tip I can give you. So rather than use the divide button, put it using your fraction button in the calculator. So you put it all together and it'll spit you out 0.17. If you were to practice that in your calculator now, if you get 0.17, well done. If you don't, keep pressing buttons on your calculator until you know what's going on. But yeah, that fraction one's useful and you need that one there. Okay, next part. We've got temperature in Kelvin and the luminosity of the sun. And what we can see is a weird scale where the temperature increases as we move that way. So the temperature is decreasing on this scale, and they're trying to catch you out because it's an exam board and they're a bit miserable. So estimate the temperature of the sun. Then we want the temperature bit, so we want to read the x-axis, draw a line down. I get that at about, if I was to split that in half, so that's 7,500, 6,000, 6,500. I've gone for 6,000. I reckon 6.5's probably a bit closer to it. I think you could have anything between 5,500 and 7,500. So that's a nice easy one there. State out the brightness, how brightness changes with temperature. So we can see luminosity. This is a bigger number than this one, and we can see that luminosity increases. So as we increase the temperature, luminosity increases, and they're just trying to catch you out of that stupid scale. So as temperature increases, brightness increases. Just get in that habit as increases or decreases, increases or decreases. Get in that habit of doing that. State how brightness changes with mass. So let's go back and have a look. Low mass, high mass. As mass goes up, luminosity goes up. So as mass increases, brightness increases, or luminosity increases. Next one, nuclear fusion provides the energy for stars. So we know, let's take two small nuclei. We're going to join them together. In the process, this is going to go on to give us bigger and bigger and bigger and bigger nuclei, and it's then going to make a neutron as well. And in the process, when this takes place, a tiny little bit of mass is going to be lost, and that's going to be converted to energy according to Einstein's E equals mc squared. And 3 times 10 to the 8 squared is a pretty big number. So small nuclei, such as hydrogen, are joined to produce large nuclei and a neutron. High temperature and pressure are needed, so the nuclei are positively charged. They don't want to be near each other. So we've got to have a ridiculous high temperature and pressure to squeeze those together and to overcome that repulsion. And in the process, a small amount of mass is lost and converted to energy according to E equals mc squared. Now, this isn't exactly the same as the mark scheme. Obviously, I'll give you that to mark your paper. I think this is a nice answer to just always use. On to the next one. You've done this to death and you're brilliant at it. So a nebula may evolve into a main sequence star. Explain how it may happen. So in terms of that basic, we did loads of drawing and we just said big star explodes and we've got dust and gas, but in one area there's slightly more. This is going to form the center of that solar system and the star. Let's just change my color if I can. So what's going to happen now is this is going to pull other areas because this has got an increase in gravity and an increase in density. Because I'm pulling this particle inwards, I'm transferring GPE into KE. This is now going to increase the temperature, increase the pressure, and then fusion will take place, which is the answer we just did before. And what we really need to be saying here is gravity is doing this work. We've got this increased gravity in this spot here, and that's going to do work. So we've learned fat, wobbly dinosaurs, and we know work equals force times distance. And the force is gravity. So we could rewrite that as work equals gravity times distance. So gravity is doing work. This is then going to pull this, increase the density, and this is going to compress the gas. So work is done to compress the gas. And that really helps every single time. Work is done to compress the gas. So a nebula is a collection of dust and gas, and it's randomly distributed. In one little area, there's more particles, so there's increased density. Because of this increased density, there's increased gravity in this area. This force of attraction will pull particles towards this area. So work is being done to compress the gas, force times distance or gravity times distance, because gravity is the force. Temperature and pressure will increase until eventually fusion takes place. And I said to you in lesson, I'd love to be there at that moment where a star was born in that first instant of fusion. It would be marvellous. And I believe that's the end.